Welcome to our new video in engineering mathematics. In this video, we will continue with our examples in solving systems of linear equations. Let's get started. So here we see an example and we have three equations in this system and three unknowns x1, x2 and x3. So as we have started doing in the last lecture, first we write the coefficients in a matrix, and then the right hand side of these equations is added to our augmented, the so-called augmented matrix. So as we see here, this is our coefficients in the system, and these are the values that are on the right hand side of each equation. And we call this representation together the coefficient matrix and the right hand sides. We separate them with this line, and we call this notation of representing these together as the augmented matrix. And we use the Gaussian elimination technique. In the Gaussian elimination technique, note that we want to make the below the diagonal, so this is our diagonal here, we want the below the diagonal terms all equal to 0. And once we are able to do that, we can directly solve the third unknown variable x3 from this equation that we will get. Okay? And in order to do that, we prefer to have the initial, the leading term in the first row of this matrix equal to 1. If we can get this equal to 1, and in this example it is already given as 1, so we don't need any extra operations here, it is already equal to 1. So what you can do is, for example, we can multiply the first row by -3, so each term is multiplied by -3, and then we can add that to the second row. This will allow us to get this leading term equal to 0, and that's what we want. But we also want the leading term in the third row to be equal to 0. And similarly, the second element in the third row, we will also try to make it equal to 0. And in the Gaussian elimination method, actually we are doing row operations in order to achieve this, because the equations, the system, and the solution of the system doesn't change as we do these row operations. So you can do the first row operation as we said, multiply the first row and the right hand side with this -3, and then add that to the second row. Then what we will get here is going to be 8 minus 2 times -3, that's given by 2, and then 7 minus 3, we get 4. Similarly, you can multiply the first row by -2 and then add to the last row, then this will become 0, 3, and 7. And we have 15 here. So 23 minus 4, minus 8, that's 15 here. Now we can simplify this a bit more, because we see this is 2, 4, and 8, because this is just actually an equation, and we can divide the left-hand side and right-hand side of the equation by 2, which doesn't change anything. So we can write that as 0, 1, 2, and 4 on the right-hand side after this simplification. And now we can make this leading term, the second leading term in the third row, equal to 0 by multiplying the second row by -3 and then add to the last one. So this will become 0, and this will become 1, and we get 3 here. Now we got what we want. So all of the below the diagonal terms here, we get them as 0. So 1 times x3 equals to 3. That gives us x3 equals to 3 from this last row. And then you can write the second row, x2 plus 2 times x3 equals to 4. But since x3 equals to 3, then we get x2 equals to minus 2. And finally, just plug in all the previous values, and then we find x1 equals to 5. In the Gauss-Jordan method, we still do similar row operations, but we try to get all these diagonals equal to 1, and of the diagonals, we try to get them equal to 0. If we achieve this representation, then the solution is directly obtained as the 1 times x3 equals to 3, 1 times x2 equals to minus 2, 1 times x1 equals to 5. So this gives us again the same result. So we can use either Gaussian elimination or the so-called Gauss-Jordan method. Here's another example. We have 5 unknowns and we have 3 equations here. And our approach in the Gaussian elimination is still the same. We write down these coefficients and write down the right-hand side. And then start to do some row operations. And we will try to get the below the diagonal terms equal to 0. And that will allow us to get the solution more easily. And once we write down our augmented matrix A given the right-hand side of these equations as B, now we start to do our row operations. We can multiply the first row by minus 2 and then add to the second row. That will make this 0, 0, 2, minus 1, 8, and minus 13. And similarly, you can multiply the first row by minus 3, and then you can add to the last one. These two terms again become zeros, and then 10 minus 9, 1, 6 minus 6, we get 0, 5 minus 3, we get 2, 27 minus 30, we get minus 3. Remember, we also want to get this term equal to 0 in order to solve the system. And we can always also swap different rows of the matrix with each other. And here we are actually swapping the third row and putting it in the second row, in the second place. And then the second row can be written as a third row. But notice that we can multiply this third row actually by minus 2 and then add to the other one. So this will make the leading term all in the first 3 positions equal to 0. So this becomes 0, and then we have minus 2 plus 1 as minus 1, and then so actually there's a change of sign here. Okay, we just change the sign. Actually we can also write this as minus 1, and this one plus 4, and then this one minus 7. So you can multiply both sides of the equation if you want with a minus sign. Again, doesn't change the result. or you can swap two different rows with each other. Again, it doesn't change the result of the solution. So these are all possible operations. And importantly here, what we observe is we have 5 unknowns and 3 equations. And once we do these row operations, we realize that actually this system is underdefined with fewer number of equations than the number of unknowns. So actually by itself here we have infinitely many solutions, but we can do some parameterization. In other words, parameterization here serves as adding extra equations into the system to complete the system to 5 equations and 5 unknowns. So here is what we can do. We can parameterize actually 2 of our x values. This essentially serves as adding 2 more equations to complete the system to 5 equations and 5 unknowns. And this is actually a choice. You can let x2 equals to s, x5 equals to t, but this is not a unique choice. I mean, you can choose x3 equals to s, for example, and x4 equals to t. Doesn't matter, because the rest of the variables will be determined accordingly by solving the system given the parameters s and t. So once you let this arbitrary real number s and t to represent x2 or x5, then the rest of the variables will be obtained accordingly. Okay, all these variables are solved with respect to s and t. And we can represent this solution of x as a, as a vector notation, where we have the coefficients 5 plus 2s minus 3. This is actually x1 in the first location, and then we have x2, x3, x4, and x5. Another example, here let's look at, similarly we have a 3 by 3 system where we have 3 unknowns and 3 equations. And if you want to do the Gaussian elimination or Gauss-Jordan method, in both you will have to do some row operations to simplify this expression. So the row operations, you start by writing the coefficient matrix, the right-hand side, and then now you should think about how to make the leading term here equal to 0 and this one equal to 0. We will try to get these equal to 0 by doing the row operations appropriately. We can multiply the third row by minus 2 and then add to the second one. Then this will become 0. This second term becomes 0. And this becomes 5 and 35. Here we have another line. I forgot to draw this. And then you can see once you get 0, 0 here, actually this can be simplified because this is 5. This means 5 times basically x3 equals to 35. But we can divide by 5, so this becomes 1 and 7. So we can divide both sides of the equation with the same number, so it doesn't change the solution. This operation doesn't change the solution. So as you see, we can take the second row as the first one. So we have our 0, 0, 1 here. And then we have the third row remaining the same. This is our second row, and then we have the first row. The first row here, as you see, if we basically subtract the last one, right? If we subtract the last row, this can be written as 2 minus 4, 0, and 10. So in the Gauss-Jordan method, as remember, we also want to make this equal to 0, the off the diagonal term. And that can be done in this example by subtracting the third row from the first one. And we get these coefficients 2, -4, and 0. The right-hand side becomes 10. And now we can simplify this first row by dividing everything by 2. If we divide everything by 2, then this becomes 1, -2, 0, and 5. Okay, so the next thing is basically now we can go to the next slide. The next thing is we can actually we can multiply the first row by 2 and then subtract from the last one. But that will become, so if I multiply the first row by minus 2, let's say, and then add to this guy, so you will get 0, 0, 0, and then right hand side, right, is also 0. As this is what we observe here in this row. But this means this is always a true statement, because 0 equals to 0. That's always true, right? What we imply here is always true. So essentially our system has 2 equations and 3 unknowns. So that means we need to introduce an extra parameter to the system, or extra equation into the system, to make it solvable. So as we did in the previous example, we can do a parameterization by letting x2 equals to t, and then x1 and x3 is derived accordingly. Another example, suppose we want to use the Gaussian elimination to solve this system, and you have a 3 by 3, that is 3 equations and 3 unknown system. So we will write the coefficients as usual, and we have our right hand side. So now we can divide, actually not divide, but sorry, we can take the second row and put it in the first location, because remember, we want to utilize this leading term in the first row equals to 1. If we have that, then we can multiply this first row with any number and then try to make the other leading terms equal to 0. That would be easier if you have 1 in the first leading term, okay, for the first row. And we can achieve that by doing the swap first. That's more convenient. And we will we write this first row, right? First row goes to the third row. So you can, for example, multiply the second row with -3 and then add to the first one. Then this will become 0. You have -2, and -6. Okay, and then the right hand side is going to be -7. So what we obtain is basically the first row goes to the second one after we do the addition, and then for the third row we can multiply the second row by -5 and then add to the third one. Again, this will be 0, 1, 3, and 3. So this is the third row that comes here after this row operation, of course. So we can multiply the second row with -5 and then add to the third row. This is what we get. Now, as a next step, you can swap these two rows with each other, and we can actually multiply the second row with 2 and then add to the third one, and that will give us the 0, 0, 0. But this time we have the problem that 0 can never be equal to minus 1. So actually this is inconsistent, and there is no solution for this system. Let's do another example. In this example, you have a system of 3 equations and 3 unknowns. The coefficients are given, so you write them in your augmented matrix included with the right-hand side of each equation. And if we are using the Gaussian elimination, then we will start to do some row operations. Remember that it is always better to start with 1 in the first leading term for the first row, and in order to have that, we can put this as the first row, and then we have the first row becoming the third one. So there is a swap of orders here. And as usual, the goal is to make the below the diagonal terms equals to 0, and we can do that by adding the first row. We can add the first row to the second one, so this will become 0, 3, and minus 1. So this is our new second row after we add. And then we can multiply the first row by minus 2 and then add to the last one here. And that will become 0. So we will have, we will have 0 minus 3 and then plus 1 equals to 1. And now finally we can do one more row operation, and that will actually allow us to make the third row equal to 0, 0, 0. And this implies the last row is always true. So in other words, the number of effective equations in this system is 2. Okay, because the third row, which implies the third equation, is just always true. So it is not binding. It doesn't give any extra information. And we can, in this type of scenario, we can actually parameterize the solution, and we write down the solution for x1, x2, and x3, given the basically parameterization that we use. Here we are using x3 equals to r, x2 equals to minus 1 over 3 plus r times 5 over 3. And x1 is also calculated, derived, based on the starting value for x3. Another example, here we have a system of equations, but the system depends on some real constants, lambda and beta. Beta is also here. So the question is, according to different scenarios, what should be the lambda and beta value for this problem? So as usual, we can write down our system of equations with the coefficient matrix and the right-hand side given. Notice that this is lambda plus 1, and we have beta as the two unknown coefficients in this representation. But we can start as usual and try to get the leading term in the second and third rows equal to 0 by doing some row operations. And as you see, the row operation we can think about is we can multiply the first row by minus 1 and then add to the second one, and then we can also add it to the third one. That will make these leading terms equal to 0 here. So this becomes 0 and 0. And basically we have minus 1, 1, beta minus 2 in the second row. And then for the third row we have minus 1 times minus 3. So that's plus 4 plus 1. So sorry, 3 plus 1, that's equal to 4 here. And then we have lambda plus 1 minus 1, that equals to lambda. So once we sort out this form and do the row operation as usual, now it simplifies like this. Another step is we can multiply the second row by minus 4 and then add to the third row, because we also want to get this term equal to 0. So this becomes 0, and then we have lambda plus 4. Right hand side we have 4. We have 4 beta minus 4. So we multiply this by with plus 4 and then add. So basically we have 4 beta minus 8 plus 4, that's 4 beta minus 4. So now the important thing is, depending on the values of lambda and beta, whether we can have a unique solution, inconsistency, or infinitely many solutions change. And the first scenario is, let's say, if both of them are equal to 0, then this is 0 equals to 0, and that's the basically infinitely many solutions case. So we can easily identify if both of them are given by minus 4 and beta equals to 1, then we have the third equation effectively doesn't say anything, which is always true, right? If the left and right hand sides are the same. So basically we end up with infinitely many solutions in that case, because essentially we will have 2 equations and 3 unknowns. So the system is underdefined. But if we have lambda equals to minus 4 and beta is not equal to 1, then this becomes an inconsistency and therefore no solution in this system. And the third possibility is if lambda is not equal to minus 4, but beta is just any real number, then this gives us a unique solution. Another example. Here we have 2 equations and 2 unknowns, and we want to analyze the solution with respect to different values of k. And as usual, we start by writing the coefficients. But pay attention that this time, for this example, the right-hand side values are all equal to 0. So for this type of equation system, we have the homogeneous system. We call this as the homogeneous system. But in the homogeneous system, the trivial solution, that is all these unknown variables x and y equal to 0, that is a solution, and that's called as the trivial solution. So here the augmented matrix is written, including the 0 right-hand side values. And then just do your row operations as usual. So you can multiply the first row by minus 2 and then add to the second one. That makes this 0, k minus 4, and 0. Now, we can do the similar analysis. For example, if k equals to 4, that means 0 equals to 0, which is always true. And we have infinitely many solutions in that case. In other words, if we have k minus 4 equals to 0, so that k equals to 4, of course, this will become essentially one equation, 2 unknown system. And the other case, if k is not equal to 4, then basically we will get the second variable y equals to 0, and therefore x is also equal to 0. So this is actually the trivial solution for this type of problem.